I'm going to take over from Usman and going to talk about some of the papers in the special issue that dealt with the problem of distributed optimization. And these are some of the papers. Some of the other papers will be dealt with by Dr. Mike Rabat, who is also going to focus on many of the practical aspects of these problems. So let's get started. So we have a number of scenarios in the real world where we are collecting a lot of data, and the special issue tried to focus on three different scenarios where we use data to do distributed learning. So one of the scenarios looked at this edge computing system or sensor network system, where the idea is you have these devices that are collecting a large amount of data coming from different sources, and then you are trying to make some kind of automated decision using machine learning or artificial intelligence. And all of those things at the end of the day, as Usman mentioned, have to rely on some sort of optimization. So you have this setup where you are trying to do optimization in this framework. Another framework that arises, which has become very popular in the last 5 or 6 years, driven largely by the concerns for privacy, is what is called the federated learning setup, where the federated learning, for example, in this case, think of the example of hospitals, where there is value. Every hospital has their own data set, and there is value to leverage all this data for decision making, except that there are privacy concerns that you don't want to actually share all the data at one location. So federated learning is a setup where there is some central coordinator that is trying to help you do this learning without ever exchanging data between or sharing of your data explicitly. So again, if you are trying to do, for example, machine learning tasks, if you are trying to figure out, well, how do we leverage all the MRI images in different hospitals to develop a machine learning based diagnostics that can help the physicians, not replace them, but help them, that will still involve the issue of not being able to share the data, and you can then try to run a machine learning algorithm that actually does this in a distributed fashion without ever sharing the data and keeping into view the privacy concerns. The third setup that arises, which is being used a lot in the industry, especially in large companies like Facebook and Google and Amazon, or anyone which has a very large scale, as Mike would talk more about that, is this setup where the data is under your control, but because of the scale of the data that you have, you can't store it in one machine, so you can't do learning in one machine. So you have this what is called the master worker architecture, where there is a central server that is basically communicating with these worker nodes. Every worker node has its own set of database that they are maintaining. And the whole goal in this setup is to speed up the computation times. So all of these problems involve some sort of distributed data sets located at different entities, machines, devices. They could be physical entities like hospitals. And the reason you don't want to share data are different. The objectives that you have at the end of the day are a little bit different. For example, in this setup, the goal is to do faster processing. In federated learning setup, the goal is to maintain privacy. In the edge computing setup, you cannot share the data because the bandwidth might be constrained and so forth. But a lot of these problems end up having a general abstract framework of what is called distributed optimization. And the way you can pose that problem is you can think of that and here I'm just taking the example of the master worker architecture, but similar ideas can be, the same formulation applies to the other two setups I talked about, with a few other caveats that you have to take into account. So I'm just abstracting it into one formulation. So the idea becomes that, let's say this is node 1, which has dataset Z1. This is node 2, which has dataset Z2, and this is node N, which has dataset Zn. So each one of these, for example, if you are doing, again, take the example of you're trying to learn a classifier, each one of these has access to, can make, given a classifier X, can come up with some loss function, which is F1. It is F1 because it is dependent upon the data of this database Z1. This is a loss function F2, and this is a loss function Fn. Now, of course, each one of these nodes could individually just train their own data set and come up with a solution, but that solution won't be the optimal because you are relying on a far fewer data samples. And as we know, the rate at which a classifier will converge to the true solution is a function of the number of data samples you have. So you don't want to throw these data samples. So the actual goal is you want to actually find, you have a collective loss function, which is given by sum of all of these individual loss functions. So capital F is simply sum of FJs. This is called a separable optimization problem. Each FJ exists in individual node. And the distributed optimization problem basically tries to find the solution, or in this case, the classifier. You can extend that to any other objective formulation, optimization objective formulation, uh, that minimizes this objective function, which is divided among n nodes, perhaps subject to some constraint X. For example, if you are doing principal component analysis, this constraint could be that the solution you obtain must correspond to orthogonal basis for the subspace you're learning. So this is the general abstract framework that the special issue addresses through 4 papers. There are, as I said, additional papers that Mike Rabat will talk about. But within this formulation, we had 3 papers that looked at deterministic optimization problems, where we said that the objective function f is completely known, or it is deterministic. And so paper number 1, 2, and 5 in the special issue, we'll talk more about that. And then there are paper number 1, 2, and 8 talk about stochastic optimization problems, where the idea is that the information about the objective function comes with some uncertainty. So maybe it's a gradient that is noisy, or the evaluations of the functions are noisy. And that is the setup in many machine learning problems, where you are trying to find something which is best for a statistical distribution, and so you go to the stochastic optimization problem. So within diving further into the 2 distinctions that I have made within the special issue, we had distributed deterministic optimization, paper 1 by Shin et al., 2 by Sahu and Carr, and 5 by Franca and Bento. And these papers discuss several research problems and left open questions about several other research problems. In particular, these papers focused on both convex and non-convex objective functions. So the total objective function capital F, which is given by summation of these little f's, that could be convex or non-convex. These papers looked at both constrained and unconstrained. Some of them just focused on unconstrained, some looked at constrained problems. And then between them, they looked at zeroth order methods, where you couldn't compute the gradients explicitly because the analytical form didn't exist, or other reasons. It looked at first order methods, which just relied on the gradient information. And these works, especially paper number 5, looked at proximal based, or ADMM, or primal dual methods. So 3 different class of methods. These papers then try to provide solutions and discuss strategies that you could use under 2 constraints. One is where the communication is symmetric and two-way. The other is where the communication is asymmetric, or what is called directed graphs. So maybe node A can talk to node B, but node B cannot talk to node A, things like that. And the questions that were addressed were, what is the interplay between different optimization problems and convergence rates? So for example, if you have strongly convex problem, or if you have a smooth convex problem, or a non-convex problem? What are the kind of convergence rates that you get? What is the topology, especially paper number 5 looked at what is the interplay between the topology. So how does the topology of the network affects the convergence rates? And some of it probably Mike would also discuss a little bit in terms of practical aspects, but that comes up if, let's say, you are building a master worker architecture for speeding up your network. Is the star topology the best topology, or should you look at other topologies for various other reasons? These works did not always end up addressing a number of other questions, which are some of the questions that are of great interest to the community. They include second order convergence guarantees. So can you confirm that the solution has reached at least a second order solution and has not converged to, let's say, a saddle point? These works did not look explicitly at asynchronous communications. Some of them didn't look at time-varying network topologies. What happens if you have malicious attacks on some of the nodes and things like that? They were not looked at in these works. The other body of work looked at distributed stochastic optimization. There were 3 papers that looked at it. Again, Shin et al., Sahu and Carr, and Nokalby et al. In these works, similar to the previous case, they looked at convex and non-convex objective functions, unconstrained and constrained optimization, and zeroth order method, first order methods. And then paper number 8 talked about stochastic approximation methods explicitly when you are trying to solve the distributed stochastic optimization problems. These papers basically looked at stochasticity arising in 2 contexts. One is you are trying to do some sort of like an empirical risk minimization problem, which is what people do for most often in machine learning problems. And the stochasticity, the randomness arises because the gradient computations are random. You can't always calculate the true gradient for various reasons. The scenario 2 looked at, which was addressed in paper number 8, is if you have streaming data problems. So the data is continuously streaming, and the stochasticity arrives because of that. And then the solutions were looked at in terms of symmetric two-way communication and asymmetric communications. The things that these works addressed involved stochastic noise. So they looked at the interplay between classes of optimization problems, convergence rates, and stochastic noise. So how much noise is the noise variance, for example, how is that going to impact the solution and how good that solution is going to be? It also looked at, some of these works looked at the explicit question of this idea of what's called mini batching, which is that there are these 2 extremes where you can have full batch, where you process all the data together, which gives rise to deterministic problems, or you process one sample at a time, or the stochastic gradient descent. And then there is something in between, which is mini batch stochastic gradient descent, which is where you collect, instead of one sample, you collect maybe 10, 15, 20 samples. And there's an important question of how much the mini batch size should be so that you get to the right solution. These works looked at also what is the effect of streaming rate, communication rate, and computing capabilities of individual nodes. What's the interplay on the solution? Also, statistical accuracy. Again, a number of problems remain unaddressed, in particular, second order convergence guarantees, effects of straggler nodes, asynchronous communications, and malicious attacks. I could go further into a particular aspect of streaming data to basically highlight the interplay between the streaming rate and the communications and computation. But in the interest of time, we can come back to this question. I would perhaps skip it at this point, and we can come back to it if there is an interest during the Q&A session, because we want to leave enough time for that. I will, at this stage, hand it over to Dr. Michael Rabat from Facebook, and he will talk about some extension of what I talked about, and also many practical aspects and applications. So over to you, Mike.